Welcome to the next lecture in the signals and systems. So in the last class we solved the different problems based on the convolution integral. So here in this lecture we will discuss the different properties of the convolution integral. So to start with, the first property is called the commutative property. So the convolution operation possesses the commutative property which is written in this way: xt convolution ht will be equal to ht convolution xt. Okay, so this property you can see that it actually implies the role of the input signal and the impulse response are interchangeable. So we can interchange these two different signals xt and ht. Okay, the second property is the associative property. So this convolution product or convolution integral is associative also. It can be represented in this form. Okay, so if we have three maybe different signals xt, h1t and h2t. Okay, so this convolution operation is associative also. So if you do the convolution of h1 and h2 and then convolute it with xt, so this will be same as first convoluting xt and h1t and then convoluting the resultant signal with h2t. Okay, so this implies that a cascade combination of LTI systems can be replaced by a single system whose impulse response is the convolution of the individual impulse responses, isn't it? So that means that let's suppose that there are two different systems. This is h1t and this is h2t. Okay, if this is the output, this is the input signal xt, so this is same as h1 convolution h2 so this is the meaning of this associative property. Now come to the third one, that is distributive property. So this convolution operation also possesses the distributive property. It can be shown in this particular form. Okay, so this property shows that a parallel combination of LTI systems is equivalent to a single system whose impulse response is the sum of the individual impulse responses in the parallel configuration. I will try to show it with a block diagram. So this is H1 and this is H2. This is XT. So this is same as okay. So that's what I said, that a parallel combination of LTI systems is equivalent to a single system whose impulse response is the sum of the individual impulse responses in the parallel configuration. So these are the individual impulse responses H1 and H2. So this can be equivalent to a single system, and the impulse response of this is the sum of these two individual responses. Okay, so this is the meaning of this distributive property, you can say. Next is the shifting property, or we can also call it as shift property. Now according to this shift property, if xt convolution ht equals to this yt, then xt convolution h t minus t naught is equal to x t minus t naught convolution ht equals to yt minus t naught. And one more thing, that x of t minus t1 convolute with let me just erase this, convolute with h of t minus t2 will be equal to y of t minus t1 minus t2. Okay, so you can see from here that if this is the convolution result which is already defined, that is the convolution of two signals xt and ht is yt, that is already with you, and then the convolution of this xt minus t1 and ht minus t2, that means that if there is a shifting in any one of the input signal or in the both signals, then the same shift will be represented, and the same shift will be occurred in the output signal as well. So you can see from here that if there is shifting in this ht signal, that is t minus t naught, or there is a shifting in this xt signal again of t naught, then the same shift will be in the output signal. Output signal will simply be represented as yt minus t naught. Or if there is a shift in both the signals, t1 is the shifting in xt signal, t2 is the shifting in ht signal, so the total shift in the output signal will be equal to t1 plus t2, that is y of t minus t1 plus t2, it can be written. Next property is the convolution with an impulse signal. So the convolution of a signal xt with a unit impulse function results in the signal itself. So this can be represented in this way, that xt convolution with impulse signal is equal to the signal itself. So this is the property of, you can say, a signal, that whenever it is convoluted with an impulse signal, it will give you the original signal itself. Okay. Next property is called the width property. So the width of the you can say the non-zero extent, which is the interval of time between the first and last non-zero values of the continuous convolution of two functions, equals the sum of the widths of the non-zero extents of the two functions. So let us try to simplify it. That, in other words, if the duration or the widths of xt and ht are finite, that means, let's suppose that signal xt has a width which is equal to wx, it is some value of wx, okay, and ht also has a duration or width which is represented by this wh, okay. So then the duration or the width of the convoluted signal xt and ht will be equal to the widths of both two signals. Okay, so this is quite straightforward, that whatever be the widths of two signals, the width of the resultant convoluted signal will be the sum of the widths of these two signals. Okay, so we can also see a problem based on this. Let's suppose that these are two signals. This is xt, amplitude is 1, from -1 to 3. So this 1, 2 and 3 we can write like this. Similarly, in this second one, this is 1, this is 2, 3, 4, okay. So this is ht and this is xt, okay. So let us suppose that if these are two continuous time signals xt and ht, which is represented by here, and you have been asked that where will the right and the left edges of the convolution of xt and ht be located, and what will be the width of the non-zero extent of the convolution. Okay, so you can just use these different properties, the width property which we have discussed. Then the if the right edge of this xt, you can see that the right edge is 3. So right edge of this xt signal is 3. Similarly, right edge of this ht signal is 4. So you can see from here, let us just denote it in this simple way. The left edge of the xt signal is -1 and the left edge of ht signal is 0. Okay, so then the duration of this xt signal. So what is the duration? So duration can simply be represented just as counting these values, or just subtracting the left from the right edges. So duration will simply become as 4. Okay, and similarly the duration of this h2 signal will be equal to 4. Okay, so it will be 4 as well. Now when you will convolute these two signals, that is yt, when it will be convoluted as xt and ht, okay. So what will be the right edge of this convoluted signal? This is what is being asked in the problem. So right edge of this convoluted signal will simply be the summation of the right edges of xt and ht. Okay, so the right edge will be equal to 3 plus 4, 7. Similarly, the left edge of this convoluted signal yt will be equal to the summation of the left edges of xt and ht signal. So it will be minus 1. Minus 1 plus 0 will be minus 1. And what will be the width of this yt? So width of yt will be equal to the width of the two different signals x and h. So 4 plus 4, that will be equal to 8. Okay, so this is how this problem can be solved. So this is not the exact answer of convolution. We have just evaluated the different limits, you can say, the different edges and the different widths we have just obtained. For obtaining the original convolution, you have to know the function values, the mathematical relations, and then you have to solve it in the way which we have discussed in the previous lectures. Okay, next property is the differentiation property. So differentiation property states that if the convolution of xt and ht is equal to yt, then the convolution of the derivative of the first signal with ht or the convolution of the first signal with the derivative of second signal will be equal to the derivative of the output signal. Okay, so if the convolution is already known and if there is a differentiation in the any one of the signal, then the output will also be the differentiated value of the original result. So this is the differentiation property. Next is the time scaling property. So time scaling property can be written as according to the time scaling property, if xt convolution ht is equal to yt, then the convolution of the time scaled version of the signals will result in this signal. Okay, so 1 by mod a y of at. So pretty straightforward meaning of this property is that if both xt and ht are time scaled by a, then their convolution is also time scaled by a and multiplied by 1 upon mod a. Okay, so this is the meaning of this property. Okay, now before going further, I would like to discuss 2 or 3 important points. Okay, these will help you. These are just some extra things, that the convolution of an odd and an even function is an odd function. Okay, so let us suppose that there is an odd function and it is convoluted with an even function, so the result should be an odd function. Similarly, if the both signals are odd functions, then the convolution of these two odd functions should result in an even function. Or if both the signals are even function, then also their resultant should be an even function. Okay, so here this operation represent the convolution operation. Okay, so these are some extra things which you may know. Okay, so just simply you can see that if the two signals are same, either they can be odd or they can be even. So if they are same, if both are odd or if both are even, then the final convoluted operation should be even. And if they are different, like one of them is odd, the other one is even, then the final convoluted operation is an odd signal. Okay. One or two important results I would like to share with you that will be needed in solving some problems. One of the standard relation or standard result of the convolution operation, that if xt is convoluted with del t minus t naught, then it will come as x of t minus t naught. Okay, and similarly, if x of t is convoluted with del t plus t naught, then the answer will be x of t plus t naught. Okay, so these are the standard results which you may memorize, although the derivation is also present in the book. So if you are interested, then you can also see the derivation for it. So before just concluding the lecture, let us quickly see one short problem, that is the convolution of two unit step signals. Okay, ut when convoluted with ut itself, what you will get. So if the unit step signal is convoluted with itself, okay, so it can be solved in a simple way. Just write down the convolution integral for it. Okay, and since you know that u of t minus tau equals to 1, this is for t minus tau greater than 0. Obviously this is from your previous knowledge of unit step signal, you know, and this is, otherwise it is 0. So therefore we may write it as the convolution of these two is equal to minus infinity to t u tau d tau. Okay, because it is only defined up to this t. For all the other values it will be 0. So amplitude, you know, amplitude will always be 1 since it's a unit step signal and it is defined from 0. So it will just make this lower limit as 0. So 0 to t. So it will be t for t greater than equal to 0, and it will be 0 for t less than equal to 0, and which is equal to ramp signal. So if you clearly see this function which is written over here, so this represents a ramp signal, isn't it? So we can write the convolution of unit step signals is a ramp signal. Okay, so with this much we stop today, and we'll discuss the rest of the things in the coming lectures. Thank you very much.